Projectiles, inclined plane, type 2, vertical landing. So here we have a plane is inclined at an angle of 60 degrees to the horizontal, and the particle is projected up the plane with an initial speed of u at an angle of theta to the inclined plane. So again, we always have to be careful with our inclined plane questions. Is the angle with respect to the plane when it's being projected, or is it with respect to the horizontal? Because if it's with respect to the horizontal, you end up with the angle minus the angle of the inclined plane. But here it's given to us with respect to the plane. Now the key to this question is the fact that we're told that the particle strikes the plane at right angles. So what this means is that it's landing vertically. So if we draw a diagram of what's happening, so we can see that we have the plane is inclined at an angle of 60 degrees. We're given the initial speed is u, and it's projected into the air, but on landing it comes down at 90 degrees. So the angle with respect to the plane then is theta, and the speed is u meters per second. Okay, now just as a side note, you have to remember when the particle is landing normally, if it's not landing at an angle of 90 degrees, then here's your landing velocity, and you'll resolve that into your y and your x components. And this would be your landing angle here, then L. So again, the velocity in the y direction would be negative because it's in the opposite direction to the projected direction. And the velocity in the x direction would be positive. So if you're looking at the landing angle there, then it's basically a right angle triangle where your Vy would be your opposite and your Vx would be your adjacent. So you'd end up with tan L is minus Vy over Vx. But because we're looking at it landing at 90 degrees here, then we actually see we have no velocity in the x direction. It's only in the y direction. And also on landing, we know as normal that Sy is equal to 0. So we're going to be using both of these equations for solving this problem. And a lot of time in the B parts of these inclined plane questions, we're showing some sort of a statement is true. So we're here in this question, we're looking to show the range. So we're trying to find the range. And again, that's this distance from start to the end point. In other words, we're looking for S in the x direction when the particle has landed. So we're going to need to find our time of flight. So because we have two equations here, Vx equals 0 and Sy is equal to 0 on landing vertically, then we can actually work out our time of flight in both cases and equate them, or else work out the time of flight for one and sub it into the other. So you have a choice of which you want to do or which you prefer to do. I tend to have a tendency of equating the two equations for the time of flight and then solving whatever statement it is I've been asked to do. Okay, so let's get started. So again, you're going to pause the video and check, have you got your table done out properly in the x and in the y direction? I showed you how to resolve gravity in the last example from 2006 3b. So let's hope you remember to resolve your gravity properly. Okay, so we don't know what theta is. So the angle of the inclined plane is u cos alpha. So in this case, your alpha, if I just mark it in, is theta, and your beta is your 60 degrees. So in the initial velocity in the x direction, we have u cos theta and u sine theta in the y direction. Our gravity is going to be minus g sine beta in the x direction. So of course, if we work out to the side, well, sine beta is going to be sine 60, which is root 3 over 2. And cos beta will be cos 60, which is a half. So therefore, in the x direction, our gravity is minus g sine beta. So that's going to be minus g sine 60. So in other words, minus root 3g over 2. And in the y direction, it's minus g cos beta. In other words, minus g cos 60. So minus g over 2. Our velocity is v is equal to u plus at. So in the x direction, that's u cos theta minus root 3 gt over 2. And in the y direction, that's u sine theta minus gt over 2. S is ut plus a half at squared. So s in the x direction is u cos theta t minus a half of root 3g t squared over 2. So that's going to be 2 times d, which is 4. And then s in the y direction is u sine theta t minus g t squared all over 4. And of course our time is in terms of t. Okay, so we're going to try and prove that the range is 4 root 3u squared over 13g. So as we mentioned at the start there, we're going to use the fact that we can work out the time of flight on landing when v of x is equal to 0 and s of y is equal to 0. So we're going to start with on landing, v of x is equal to 0 because it lands at right angles or vertically. And therefore we take our equation for v of x, which was u cos theta minus root 3 gt over 2. I'm going to let that equal to 0. And I'm going to solve for t. So I'll multiply both sides across by 2. So we end up with 2u cos theta minus root 3 gt is equal to 0. So getting t on its own gives me 2u cos theta all over root 3g. Okay, so this is one equation that represents the time of flight. So we're now going to repeat that for s of y, and then we'll equate the two. So we say on landing, sy is equal to 0. And we know that sy is equal to u sine theta t minus gt squared over 4. So if I let that equal to 0, and I'm going to multiply across by 4, then I end up with 4u sine theta t minus gt squared is equal to 0. I'm going to factorize out t as my highest common factor. And then I'll let both my factors equal 0 because they multiply to give me 0. So that means both are equal to 0 or one must equal 0. And getting t on its own gives me 4u sine theta all over g. So of course t is equal to 0. In other words, sy is equal to 0 at the start. And therefore this time here is my time of flight. So it's my second equation for my time of flight. So I'm basically going to take equation 1 and equation 2, and I'm going to equate the two because they represent the same thing. So we're going to equate 1 and 2. So therefore I have 2u cos theta all over root 3g is equal to 4u sine theta over g. So we'll just go back. So taking equation 1 and equation 2 and equating them. Now that's nice and handy because straight away I can see I have u is gone, I have g is gone, 2 will also go into 4. So that leaves me with cos theta over root 3 is equal to 2 sine theta. Now if I divide both sides across by cos theta, if I divide both sides across actually by 2 cos theta, then what I'll end up with is cos theta over 2 cos theta times root 3 is equal to 2 sine theta divided by 2 cos theta. And cos theta will go into cos theta, 2 will go into 2, and sine over cos is, of course, tan. So what that gives me is tan theta is equal to 1 over 2 root 3. Okay, so how is this going to help me get what it is I'm trying to prove? Well, I'm looking for the range, and the range is s of x. So if I go back to my equation table, I can see s of x is u cos theta t minus root 3 gt squared over 4. So therefore, to actually get out this 4 root 3u squared over 13g, clearly I need to get rid of my cos theta and I need to get rid of my t. So I need to know something about cos theta and I need to know something about my time of flight. Now my time of flight could either be equation 1 or 2, it's the same thing. So if I look at equation 1, well again I need cos theta. And if I go for equation 2, I need sine theta. So I have tan theta, and again if I draw my right angle triangle, I have opposite over adjacent. And of course, by using Pythagoras, we can then work out the hypotenuse by getting o squared plus a squared square root, which gives me root 13, and that's my hypotenuse. So therefore, I can write down, well, sine theta must be the opposite over the hypotenuse, which is 1 over root 13, and cos theta is equal to the adjacent over the hypotenuse, which is 2 root 3 over root 13. So depending on which time of flight you use, you now have sine theta and cos theta to sub in. Okay, so let's look at our time of flight then. So I'm going to go with 2u cos theta over root 3g. So I can say t is equal to 2u, and cos theta, well that's 2 root 3 over root 13 divided by root 3 over g. So therefore that gives me my time of flight to be, well, root 3 goes into root 3, and then I'll have 2 by 2, which is 4u all over root 13g. So now I know what my time of flight is. So now I can just go and sub in to my range. So my range, s of x, at t is equal to 4u over root 13g. And my equation for s of x was, let's go back, s of x was u cos theta minus root 3 over 4 gt squared. So u cos theta t minus root 3 gt squared all over 4. So now all I have to do is sub in for cos theta, which we said if we go back was 2 root 3 over root 13 times the time of flight, which is 4u over root 13g, minus root 3g over 4 times t squared. So be careful again here, you are squaring the time. So if I multiply out my brackets, well, I have 4 by 2 is 8 by root 3. So I have 8 root 3 u squared. Root 13 by root 13 is 13g. And then I have minus root 3g over 4. If I square the brackets there, I end up with 16 u squared over 13g squared. So I can divide g into g squared, I can divide 4 into 16. So I have 8 root 3 u squared over 13g minus, so 4 goes into 16 4 times. So I have 4 root 3 u squared, because g goes into g squared. So I'm left with 13g, which is a lowest common denominator. And then 8 root 3 minus 4 root 3 is 4 root 3 u squared over 13g. So I haven't even looked at what is it really that I have to prove for my range. So I'm hoping when I go back that I have what it is I was trying to prove. And yeah, lo and behold, that's exactly what it is. So I didn't focus or put emphasis on how I was going to get to the end. I was focusing on what was the information I'm given. And these always kind of just fall out at the end. So don't ever get caught up in how am I going to figure that out? I don't know how to get the answer. It's all about what's the information provided, what's happening in this projectile, what's happening on landing, and proceeding as normal by trying to work out your time of flight. And the end then always works out nice and neatly. And sometimes you'll have to use your little bit of trigonometry from page 14, 15 or 13 in your maths tables. Okay? So in terms of the marks then, we had 5 for getting our first time of flight. We had 5 for getting SY is equal to 0. 5 for getting our second time of flight. And 5 for subbing it into S of X. And then 5 for getting the range out. So we had 25 in total. Let me just say 25 marks here. Okay.